Colin Zarzicki.
Yes.
It's about improving tropical cyclone representation in circulation models.
Well, thank you, Donna. I'd just like to quickly thank the Newton Institute and the program organizers for all their help and setting up such a great place to have PDEs this year. Like Donna mentioned, I'm going to be talking about how we can use variable resolution in GCMs to improve tropical cyclone representation. So this talk is actually going to be probably slightly more applied than some of the talks that we've seen over the last couple days. So historically, modeling tropical cyclones in general circulation models has proved to be pretty difficult. In the past, the computing constraints that modelers were given forced us to run at really low resolutions. This makes it very difficult to resolve the inner dynamical structure of tropical cyclones. And in conjunction with that, a lot of the features that drive the thermodynamic engine of these storms, such as air-sea fluxes and convection, occurred at the subgrid scale, so they required heavy parameterization, something that's obviously not ideal for getting full modeling. With that said, higher resolution studies have become a little more prevalent in the community recently. Although these still require a significant computational demand, large blocks of time on very big computers, even just to get down as low as 25 or 50 kilometers, which you can argue is really still pushing the upper end of what you'd need to really effectively model even larger tropical cyclones. As of 2012, some of the bigger forecast centers, NWP is now pushing down to 10 to 25 kilometers on a global scale. But the climate models that we're still using for the upcoming AR5 IPCC report, we're maybe down as low as 50, maybe up to 200 kilometers with some of the larger ensemble simulations. So variable resolution feature, it's been recently implemented in NCAR's community atmosphere model, in particular the spectral element dicore, and that's going to be CAM-SE. CAM-SE is actually scheduled to become the next default dicore in the upcoming release of CAM-CESM, the official release version. It's on the cube sphere grid, so we don't have to worry about any polar problems that we'd see with the standard lat-long grid, so we don't require any special filtering. And the really nice thing about the spectral element core is that it's highly scalable to 2,000s of cores. So the type of refinement that we're going to actually use within the grid is a conforming refinement. And just to go through that, every edge is shared by two and only two elements. It's an unstructured grid, so we're not using any sort of stretched or telescoping grid. This gives us a little more flexibility in our refinement. And I believe this is actually the start of the adaptive session, but we're still going to be talking about static refinements. This is the transition. So we're going to set up that grid at the beginning of our runtime, but then it's going to stay fixed through our integration. So variable resolution has been used for tropical cyclone studies in the past, limited area models. For example, a lot of the nested WRF simulations. Essentially what we want to do is apply that construct now to global models. So we want to be able to take these scalable dicores, take that computing power that we have available to us and focus it in regions that we're actually concerned about. So just a look at what one of these refined grids might look like. This is actually a very simple refinement where we actually just refine over a specific hemisphere on the cube sphere. So you can see we have a coarse hemisphere and a fine hemisphere. In this case, we're doing a 4-order refinement from a 2-degree grid, so we have a half-degree grid here in the center. This is just a blow-up of what the grid looks like. We use a meshing software from Sandia National Lab called Qubit, and it creates this type of standard meshing structure where we go from an element here, well, one element, we go to a 3-element structure. This is actually, since it's a 2-level refinement, we kind of have another 3-element structure, and then we go to these high cells. But in general, it's a 1, 3, 4 type refinement, and that's what you'll get any region that you actually refine in. A lot of the test cases I'm going to show today, we use a very aggressive transition region. So we'll do things such as kind of scale on orders and go right through this very narrow region. Essentially, our theory behind this is pushing this variable resolution feature as hard as we can push it. In practice, what you'd really want to do is have slower nested steps to give the atmosphere a little more chance, a little better chance to equilibrate as it moves through these regions. So the first test I want to show are very simple dry vortex advection tests. So we're going to actually set up a dry vortex on a sphere. So this is in the spherical system. We're actually going to have our sphere is not going to rotate. We're going to center the vortex at the equator. We don't have to then worry about any sort of Coriolis effects. The radius of maximum wind we chose for this vortex, 300 kilometers, is about the radius of maximum wind you might see for a very, very broad, weak warm core vortex in reality. The maximum wind is 23.5 meters per second. And we're going to embed it in an easterly background flow of 10 meters per second. We're going to complete 4 tests. Our 2 control tests are going to be a uniform grid at high resolution and a uniform grid at low resolution, a 1/4 degree and 2 degree. And then we're going to have 2 transition tests where we're going to actually take this vortex and move it from the high resolution region into a low resolution region and vice versa. And these are just 2 animations of the vortex moving through the transition region, so not the control cases. On the top, you have through the low into the high, and in the bottom, you have vice versa from the high into the low. On the top, you see that the vortex immediately begins to decay in the coarse region. The grid is unable to really dynamically resolve the vortex we've put in there. But then as it moves into the fine region, the decay is arrested, and it begins to relatively maintain its intensity. Down below, we have the opposite case, where the vortex maintains itself fairly well over the first couple of days, but then upon entering the coarse region, begins to follow the same decay parameters that the vortex up top follows. We can see that at the end, our vortexes, as we get over to the left side of the panel, are still relatively symmetric. We do develop some small asymmetries, mostly because, as you can see right about here, the vortex still is kind of residing in both the fine and the coarse region, so we're getting a little bit of a differential dynamical resolution, which kind of provides us with these small downstream asymmetries. So this is a plot of the column integrated vortex kinetic energy. So this is over the entire vortex. And up top here, this is it's really tough to see. I apologize for not making these lines a little bolder. But up here, this is the vortex decay profile of the vortex in the high resolution region. And down here, this is the one that's fully embedded in the low resolution region. So any case that we have in there should be bounded by these 2 control runs. And as we can see, this solid blue curve here is the vortex that starts in the high resolution region before moving into the low resolution region. And while it's in the high resolution region, it pretty much exactly matches our profile that we would expect. And the same thing for the vortex that starts in the low resolution region but then transitions into the high resolution region. Again, we have very good mapping here before it moves into the transition region. And then the nice thing is that after we switch into our alternate regimes, for example, once this one moves into the coarse grid, the coarse vortex moves into the high resolution grid, we then are able to maintain our kinetic energy and keep what's left of that vortex resolved. And then in the other case, as the vortex that was once in the high resolution mesh moves into the coarse mesh, it immediately follows the same decay profile as the initial coarse vortex did. So now we then moved on to test cases where we're actually using the CAM physics. So we're going to use a analytically derived axisymmetric weak warm core vortex, and we're going to set it up in hydrostatic and gradient wind balance. Those of you who are at DCMIP will probably recognize this as test case 5. In particular, we're going to be using test case 5.2 because we're using the stock physics from CAM 5. I do note here that the parameterization scalability caveats when running this do apply. Currently, CAM is set up to use the same physics package in each column regardless of what the resolution of that grid is. There's been a lot of work done in the last few years that show this is probably not the optimal setup. Unfortunately, this is an area of really burgeoning research, and there is no current option that's easily portable to CAM so that I can test some sort of a scale-aware physics. So this is our first test. We're going to transition that vortex seed from a coarse region into a fine region. Essentially what we want to do is make sure that this vortex is maintained properly as it moves through the transition region and then is able to give us a tropical cyclone on the other side. The reason why we choose these 2 resolutions is research has shown that at 2 degrees we're pretty much unable to resolve anything that looks like a tropical cyclone. Maybe you can get very weak warm core gyres, but they're very wide and are not resolved very well at all. Whereas in the 1/2 degree, this is where we begin to get features that look like realistic tropical cyclones. So unfortunately, we don't really have a good test case. We don't have some sort of analytic solution that should converge to or anything like that because, again, this is a very dynamic setup where you're judging the interplay of the physics and the dynamics. So subjectively here, what we want to look for is that the vortex maintains symmetry, that we don't really get any stretching or filamentation, and that it's able to produce a cyclone on the other side when we get into the high resolution region. And this is the simulation after 1 day. I should also mention that there's no background flow in this case, but because of the beta effect, the cyclone actually follows a very predictable northwesterly motion, and that's actually how we can predict how this cyclone will move through the transition region. So after day 1, we see that the vortex has actually started to weaken from its initial state, and this is expected because we're still roughly in the course region. We're unable to maintain that vortex, and it's beginning to fill in because it's not able to keep itself wrapped up. By day 4, though, we are now in the interior of that transition region, so we're starting to feel the effects of the high resolution region. And we're beginning to see a little bit of intensity. Evidence up here, this is an 850 millibar cross-section of the wind speed lat long. And then down here, this is actually a height cross-section through the vortex center. By day 6, we've now moved that vortex almost fully into the fine region, and we begin to see some pretty rapid intensification. We're beginning to see our nice symmetric cross-section here. And then by day 8, we see a fully mature tropical cyclone. We see a lot of hallmarks of what we'd expect in this cross-section. We have our calm eye. We have our tilted eye wall, so we have our divergence aloft. And then we have our wind maxes occurring at low level near roughly 900 millibars. So another test that we did with this same test case is we wanted to compare the performance in a uniform and a refined mesh. So instead of transitioning now, we're going to embed that cyclone in both of these meshes. Our uniform mesh is going to look like this. All over the globe, it's going to be ½ degree. And a refined mesh, what we're going to do is start with a 2-degree mesh and then refine a small patch down to a ½ degree. And it's going to be roughly analogous to the size of the North Pacific Ocean. So we start the cyclone and let it go and let it simulate without any other forcing on it. So after 5 days, on the top here, we have our tropical cyclone that's embedded in that globally uniform mesh, and in the bottom, in that refined mesh. And the nice thing we see here is a lot of features that these cyclones share. For example, the wind maximum in the core region is in the northern semicircle. We also see these small banding structures that are coming down here to the southeast. One here that's closer to the core of the storm, and this other one that's offset. And then by day 10, we again see good similarities. Areal extent, the storm's almost identical size, identical intensity. And we see here, for example, that our wind max has now rotated from the northern semicircle over into the eastern semicircle. This is just a plot of those cyclone intensities as measured by minimum sea level pressure, the blue curve being the uniform and the red curve being the refined mesh. And the gray shading represents an estimate of uncertainty based on where exactly you initialize that vortex in relation to the cell elements and the GLL points in the cube sphere method. And again, we see very good agreement here. The curves pretty much follow each other and eventually reach roughly the same intensity. And then we really should briefly discuss one of the reasons why we'd be interested in this would be the potential computational improvements in simulating the cyclone. So the uniform mesh actually has 5 times the amount of elements that we needed for the refined mesh. We're able to produce roughly the same features. And then it's not a great test of scalability because we're only doing this on 12 cores, but essentially the fundamental idea behind the SE die core would be great parallel scalability. And so we only needed 20.1% of the wall clock time to essentially create an identical cyclone in the refined mesh. So the next thing we did are our full aquaplanet climate simulations. We're going to use the same mesh that I just showed in the previous slides. You can actually see it overlaid here. We're going to force the climate, so it's an ocean-covered planet, so no topography, no land. And we're going to force from the lower boundary condition with zonally average sea surface temperatures, as shown here. The nice thing about this is it's a fairly simplistic setup, but then the simulation will rapidly reach a steady state, which has features which are actually quite, you can observe features that are similar to those observed in the climate system. For example, this is a plot of sea level pressure after 6 months, and you can see that we have transient high and low pressure systems here in the mid-latitudes. So one test we wanted to do was objectively look and see if we could spin up tropical cyclones on this grid. So we used the Vitart 97, this is the GFDL tracking code, to see if we could search for warm core vortices, sea level pressure min, vort maxes, etc. And we show that we're able to preferentially develop tropical cyclones in the high resolution region, and this is without vortex seeds. So we're able to show that on a regional scale, we're able to take a grid, this 2-degree grid that was unable to produce anything more than these weak warm core gyres, and produce good-looking tropical cyclones. And so this next slide here is actually we did a higher resolution time slice of that previous simulation, and I just wanted to show that we actually can produce fairly realistic looking cyclones given the physics packaging, given these refined meshes. So up here, this is a storm that we formed in the northern hemisphere during that simulation. This is the 850 millibar winds. We have a very nice symmetric, essentially the donut core in the wind field. Here we have our total precipitation rate, which is actually really nice here. So while it still looks like a giant blob, this is essentially better than most climate models have been in the past when you're running at 1 degree, for example. We're actually able to resolve a little bit of an eye feature. And we're beginning to see hints of some spiral rain bands. Our wind speed profile looks good. Again, we see the calm eye, the tilted eye walls. And we have our very strong stacked warm core, our positive temperature anomaly, up above 10 kilometers. So this is all very good. And essentially, we were able to get 25-kilometer resolution of these tropical cyclones with less computing power than we needed for a globally uniform 50-kilometer model.
Question.
Sorry, Phil. Yeah.
What are we looking at here? Is each quadrilateral a spectral element, or is each?
Oh.
I mean, I'm having trouble.
Yes. Good question. I should have clarified that. So this here is the underlying cube sphere grid, and then within each of these, there will then be the GLL points. So each of these is actually having an effective resolution that's 4 times higher, because you'll then have the spectral element inside that.
Okay, so it's a 4x4 inside.
Yes.
Okay.
Very good question. If I start plotting all of those, it kind of turns into a big mess, and it's very difficult to see underneath it. But yes, I should have clarified that.
The idea that you'd resolve a tropical cyclone on 2 mesh points just was incredible.
Yes. Sorry about that. So this is quickly an example of, so one of the things that was very difficult with the idealized test case is a lot of people have asked, well, what do the cyclones look like when they move out of a mesh? And it's very difficult to develop a cyclone in an idealized framework and then force it out of the mesh. So what we actually did instead was, as you probably noticed before, the refinement region was actually a little asymmetric, and the reason for that design was that we were able to spin up tropical cyclones in the southern hemisphere, but rather than allow them to transition to extratropical cyclones, they actually moved out of the grid, the refined grid, as warm core vortices. And so for example, here we have a nice Category 1 hurricane that was kind of moving along in the southern hemisphere, and as it slowly, over 72 hours, propagated out of the fine mesh into the coarse mesh. Again, we don't see any real observable wave reflection, no significant numerical error, and also the cyclone expectedly weakens as the grid spacing becomes larger, as we're unable to resolve that core. And in the last couple of minutes I have left, I kind of want to talk about what we've been working on for roughly the last month, especially while I've been here. So we're actually in the process of taking this variable resolution framework and using the trigrid coupler that's in NCAR CESM, the Community Earth System model. And we're going to take the variable resolution atmosphere and kind of set it up with more standard lat-long grids that are used for the ocean and land. So one thing that we've started on are AMIP-type simulations, where we have refined over the Atlantic Ocean. And essentially our goal is to, there have been some studies in the past that have looked at high-resolution CAM-SE runs and high-resolution CAM-FE runs that have looked at tropical cyclone development from a globally uniform mesh standpoint. And we're interested to see whether we can reproduce some of the interannual variability or correlations with these models with significantly less computational load. And you can see we haven't actually gotten very far with the AMIP simulations. These are just some spin-up runs. A little bit of the color has kind of gotten washed out here. But essentially, this is the region we're refining over. This is total integrated column water. And you can see that we're beginning, even after this is just a 7-day spin-up experiment, but we're beginning to develop some very fine-scale structure over here in the refined region in this field. And then the last thing that we've been working on has been using this framework to really run some high-resolution tropical cyclone forecasting experiments. So this here is actually a simulation where we use that Atlantic grid that I just showed in the previous slide, although we've refined it down to an 1/8 degree. And again, this is where this whole grid thing is going to come in. This grid here is the overlying 1/4 degree grid. And then we're actually running on an 1/8 degree grid, which then has an effective resolution below that of 4. So really, the resolution is 8 orders higher than this grid shows. But again, the more grid points I put in, the harder it is to actually see this image. So this is Hurricane Katrina in 2005, initialized on August 25th at 0Z. And the nice thing here is I have plotted in white the actual track the cyclone took. So we're still not quite on top of that track. This is using error interim reanalysis. But we actually do a pretty good job of mimicking it. We can see that the cyclone has its rapid intensification as it moves into the Gulf. And we can even start to pick up some trochoidal wobbles as it intensifies, as you get a little bit of differential in the interior core of the vortex. And then this is actually a plot of our instantaneous precipitation rate. And the really nice thing here is I showed you that plot before at 1/4 degree, and I said, oh, okay, we're starting to look a little better, a little more realistic like tropical cyclones. Well, down here at 1/8 degree, we're starting to really resolve some nice features. We have some nice spiral rain bands. We have a nice core, and we have a really calm eye where we're actually not precipitating in as the cyclone reaches its maximum intensity. And then so far, using that grid, we've gotten about a 10 times speed up over a globally uniform 12-kilometer mesh. And this is on about 500 cores. So we haven't really pushed it much further than that. If someone wants to give me the computation time, you're more than welcome. And this is something that I'd like to talk about more in detail at the satellite meeting in a couple weeks at the UK Met Office. So people who will be going there, I'll be talking a little more about this, and I'd welcome any suggestions for simulations. So just a quick summary. Our dry dynamical core tests, including vortex advection, show promising results. The variable resolution grids seem to be able to develop and maintain cyclones as they move through transition regions without significant error that we can see. If we initialize essentially identical vortex seeds in a globally uniform and a refined mesh, we're able to essentially produce identical results with significantly less computational load. High-resolution nests in our aquaplanet simulations can produce visually realistic tropical cyclones, and we can do this without vortex seeds. And then very, very preliminary 12-kilometer refined 5-day test cyclone forecasts show promise in being able, in the aspect of targeted modeling of hurricane tracks, while being able to decrease your computing load. And so with that, I'm all set.
Time for one question. Yes.
Could you explain your choice going unstructured grid using a 3 element refinement rather than maintaining structured grid with 4 squares?
Well, the main reason we stick with you mean why we're not going with like a setup where we would have hanging nodes, like why we have a conforming refinement, or? So the refinement setup is actually, that's essentially generated by the meshing software, but we need to keep the refinement conforming so that the spectral element points, the GLL points in each element, are able to maintain continuity with just one other element on a neighboring grid cell, so that we're able to maintain our accuracy and all of that. As far as the unstructured refinement, the grid itself is already unstructured grid, so there's really no reason to force ourselves to maintain any sort of structured refinement.
We have time for
Time step is controlled by the finest grid.
Yes, currently the time step is it's controlled. We have not looked into any sort of dynamic subcycling, for example, so that we can have differential time step. In general, we've done a couple tests. If you look at the elements, as long as you're refining at a reasonably high order, there isn't a tremendous amount of computational gain at this point that we can get by maybe stepping the coarse region a little less. But it is something that we are going to consider looking at in the next year or two.
Okay, let's thank the speaker again.